Hello everyone, welcome to lecture 49 of the online course on Introduction to Microwave and Optical Metamaterials. This lecture is on invisibility cloaks. So here is the lecture outline. We'll briefly introduce you to invisibility cloaks, which is an extension of the final topic of the previous lecture. We'll discuss about the cloaking mechanism and we'll go into the depth of how to design invisibility cloaks. Okay, so what are invisibility cloaks? So normally you will see that when light interacts with an object, it is either absorbed or reflected. Okay, that makes the object visible. So at its core, invisibility technology basically relies on manipulating light waves, which are responsible for our visual perception. I am talking about light waves mainly because the word invisibility comes from the optical domain itself, right? So researchers have developed innovative approaches that blend and redirect light that effectively conceals objects from view. So here is an illustration of real life invisible cloak. So you can see the person standing in front of a tree with a cloak in hand is basically invisible, okay, and the background is kind of seen, so that renders that person invisible and that person is now like kind of see-through, right. So this is an illustration. So what is the challenge? So you'll see that achieving a full blown invisibility cloak that works across entire visual spectrum, say 380 to 780 nanometer, is a huge challenge. And previously, the same concept has been also tried and tested in microwave and RF frequencies. So scientists have made fighter jets invisible to radar and also made thermal invisibility jackets, which are typically in the infrared range, that can hide soldiers from enemies' thermal cameras. But to conceal something from naked eye is really difficult because it requires some serious engineering. So true transparency would require light to pass through an object undisturbed as if the object is not at all there. So to achieve this kind of a feat, an cloaking device would basically need to redirect light from all directions around the object, so it should be invisible from every angle. So that makes it even more complicated, that you want it to work for entire visible range for all the angles. Okay, so that is where you need metamaterials, which are basically engineered materials with unique properties to play a vital role in creating this kind of invisibility cloaks. So we have seen till now that by designing metamaterials with carefully arranged nanostructures, scientists have gained control over the behavior of light waves, right? So this field, also known as transformation optics, or this is a special branch of transformation electromagnetics, it allows for manipulation of light around an object, making that object invisible. So several cloaking mechanism has been proposed and developed till now to achieve the final goal of invisibility. One approach basically involves bending of light around the object so it becomes optically transparent. The other method basically utilizes redirection of light, okay, making an object appear as if it is not there. Okay, so these techniques, they require precise control over the speed, direction and intensity of light waves to achieve this kind of effect. So now let us look into the cloaking mechanism. So I briefly discussed in the last lecture also that you basically use metamaterials for achieving this feat, where you can manipulate the electromagnetic waves, let it be light or microwave, to bend around an object so that if you look back towards the source, you will not see that object. Okay, you will just see that as if the light is coming from a source without any disturbance, right. So this is the art or the magic of metamaterial, that the waves can be guided around the object using this, right? So, how it basically works, metamaterial cloaks are basically designed with specific arrangement of sub-wavelength structures that can control the refractive index of the material. So, you are basically getting a kind of graded index material where the light can slowly bend around, okay, and then you can, when the light rays exit and if you trace back, it comes from the same source without getting any disturbance, right. So, that is basically making the object invisible. So, why this particular technology is very interesting, because it has got several applications, particularly in the field of defense. It can allow conceal military equipments from the radar detection. You can also do medical imaging that improves ability to see inside human body, that this can also be used for telecommunication purposes, okay. But once again, it is mainly attractive for stealth applications in defense purposes, right. So, a true cloak must have the following properties, as you can see here. So, ideally it should not reflect or scatter waves, and it should perfectly reconstruct the wavefront on the other side of the object. So, if there is an object and if you put a cloak around it, the wavefront before and after the object should look exactly same. So, that is how it should be able to reconstruct it. So, this is without a cloak, you see just an object in free space, you see the waves are getting distorted, giving you the signature that the wave is present here. This is the scattered wave that you see here, this one and this one, but here you see it is completely same. It is able to reconstruct the wavefront. So, the wave is not disturbed at all by this. So, most work for the waves applied from any, and another requirement is that this should also work for waves that is coming from any direction. So, there is a frequency band over which this should work. Also, it should work on for any angle, okay. So, now let us look into the path of rays, how they need to be bent to achieve this invisibility cloaking. So, our true transparency goal is that to achieve real invisibility, light coming from behind the object must exit the other side with the same trajectory as if the object is not there. So, this is the way the parallel rays are before entering the object, and this is how they should exit the object. So, whatever you do in between is the art of cloaking. So, here you can see that if there is an object placed in this square hole and this is the cloak that is bending this light beams around. So, after exiting they are exactly same as the incident light beams. That means you are able to hide the object that you are putting here, okay. So, what you are doing, instead of making a material that is making your object invisible or transparent, you are basically making a cloaking device that is basically diverting the light rays around your object in all direction, thus it is able to hide it from the view. So, here also you can see that you have a object, cylindrical object with a cloak, and then the wavefront is completely reconstructed. So, there is no disturbance created by this object, and this is what we want. Now, how to design this invisibility cloaks, and this is the reason why we have studied transformation optics or coordinate transformation, because that will be utilized in this particular example now. So, we saw that the invisibility cloaks are going to guide lights around the object, okay. So, if you want to hide this object, so what you have to do, you have to map this region into this shell region, right. In that case, okay, you can put anything inside this core region that will not be disturbing the light rays, because the light rays are not going through the core region, they are rather band around this shell region and they exit exactly in the same fashion when the way they entered, right. So, this following design steps from coordinate transformation needs to be followed. So, you begin with straight line trajectories, as you can see here in a Cartesian coordinate system which has got x1, x2 and x3 as the axis, okay. Then you convert to a coordinate system u1, u2 and u3 such that the points of a sphere with radius r, which is given as square root of x1 square plus x2 square plus x3 square, can be mapped onto a sphere of radius u, which is larger than this radius a. So you are basically avoiding the sphere of radius a. Okay, so you just want to move out of this range. So the coordinate transformation is basically mapping the points inside a sphere to the points within a spherical shell like this. Okay, and you can actually compute this kind of transformation through this linear relation. So you can say that u equals a plus b minus a by b into r. So basically whatever is within this region r less than a is now mapped within this shell region, which has got a radius of b minus a, and this is the transformation or the relationship between the old coordinate system and the new coordinate system, right. So as r will vary from 0 to b, okay, u will basically vary from a to b. Okay, so in that case, that tells you that this region is not covered here. Okay, so what you can say that this entire region of r ranging from 0 to b in the original coordinate system is now mapped into this spherical shell where the u value is ranging from a to b in the new coordinate system. So once you have known the mapping, you can also write u equals SR. Okay, so you can calculate what is this SR times R. So SR is basically the position dependent scaling factor. So SR can be written as a by r plus b minus a by b. Okay, and then when you apply isotropically, the scaling factor will give you the coordinate transformation, right. So you can write u1 equals SR times x1, u2 will be SR times x2, and then u3 will be SR times x3. This is because you are applying it isotropically, right. So this will result in points on the straight line that is having x2 equals f in the x1 equals 0 plane. Okay, that is in this particular plane. Okay, that is basically getting mapped into a curved trajectory that you see here in the u2 u3 plane. Okay, so the relationship is u2 square plus u3 square will be equal to a square times you have u2 by u2 minus b minus a times f by b whole square. Okay, so from this equation you can see the red curved trajectories which are shown in this particular figure, and that is calculated for 1 2 3 4 4 values of, you can see here 4 values of f, right. Also the grid that is shown in this particular figure C, okay, within this particular shell is computed using the equation. So the grid is no longer a rectangular grid. Okay, it is also can be calculated as u2 square plus u3 square will be equal to a square times u2 divided by u2 minus b minus 1 times f by b whole square, right. So you can find a similar equation determined by the mapping of the straight lines x3 equals f in the same plane x1 equals 0 into your u2 u3 plane, right. So finally the parameters of the equivalent material to be placed in this spherical shell of radius between a and b can be seen here. Okay, so you can obtain this from this equation. So epsilon prime, that is showing this blue shaded region, that is a new material which has got this permittivity of epsilon prime given by 1 by modulus of the determinant of A, and then you have A transpose epsilon A. Similarly you have it for mu prime, okay, and this is the transformation that you are using, where SR is given by this, and the relationship between U2 and U3 and this particular axis or the grid system is given by this. A is the Jacobian matrix that you can calculate. We have been seeing this long time. Okay, you already know how to do that. So once you compute, this is what you get. You get the new value of the material parameters, where for simplicity you can assume u to the power 4 divided by 2a u minus a square to be v square. So that is the matrix right now that will tell you the new permittivity and permeability tensor. So clearly, as you can see that it's not very easy to get this kind of a material, because the dielectric and the magnetic properties of this material in the spherical shell, which is shown here in the highlighted region, okay, is both inhomogeneous and anisotropic, right. So if you take an example on the x1 axis, that is where you have u00, you can have these values that epsilon prime by epsilon naught will be equal to mu prime by mu naught, that is b by b minus a times, then you have 1 minus u square by v square 0 0 0 1 0 0 0 1. This is the value for that. Okay. Now at these points the principal axes are aligned with the Cartesian coordinates x1, x2 and x3, as you can see. Now the principal value of epsilon 1 will vary from 0 to epsilon naught b minus a by b, as your u will vary from a to b. Okay. And while the principal values like epsilon 2 and epsilon 3, okay, they will remain fixed, because they will be simply epsilon naught b divided by b minus a. Okay. And the same thing will also apply for mu. So you will be able to get invisibility cloak, but you can see that the constraints from coordinate transformation or transformation optics resulting into the new material properties of permittivity and permeability are really challenging. Okay. So at optical wavelengths, the implementation of invisibility cloaks via metamaterials will require really advanced nanofabrication techniques such as electron beam or focused ion beam lithography. The constituent dielectric and magnetic elements, which have various shapes and dimensions, must be intricately designed and precisely laid out. Okay. Now since each element is highly resonant, the electromagnetic property of the metamaterial also depends strongly on the wavelength. So typically this kind of clocking device will operate only over narrow spectral band. So it is very difficult that you can get it over the entire visible range. So the question comes that in invisible cloaking, invisible, is it really possible? So the invisibility to radar, that is typically in the microwave to radio wavelength EM radiation, that was the first step people have achieved. But recent developments in metamaterials have actually extended this idea further. That has allowed us to bend light around the object and in a way making it completely undetectable. So recently in 2018, a novel material called broadband achromatic metalens was developed, and this is the first time it rendered an object undetectable across the entire visible spectrum. So this is a real world experimental photo where the fingers of the person is not visible, right. So the fusion of this technology with metamaterial clocking, which is and with the recent advancement in nanotechnology, that can enable the first visible light cloaking device for all the angles. So it is actually very complicated task, but the research is still in progress to achieve this particular feat. So as you can understand, that ability to bend light around an object and to show the background, and that too for incoming light from all angles and all distance, is really a complicated problem, and it can be only solved when you bring in the advances in the field of metamaterials, metal lenses, transformation optics, the nanofabrication technology, everything together. In the other field, like for the field of electromagnetics and all, okay, things are much advanced, Even a company called Hyperstealth, they are also making real life invisibility cloaking, okay, for the optical wavelengths, where you can see that there are basically 3 hammers. These are toy models, and one covered with this invisibility cloak, which is showing you the background but not the hammer, right. So here, by bending the light around an object, you can see that you can make a 3D cloaking device. So a new advance in meta lenses, if successfully applied, could extend a cloak to the visible light portion of the spectrum, and that will be the first realization of true invisibility cloak. Okay. So here you can also see that this is the sheet that is covering this tank. So from the front you can't see it. Okay. So this is also one application of this hyper stealth. They also call it quantum stealth, okay, that makes invisible military becoming a reality. So what you see here, that when successfully cloaked, an observer from any angle or location could see only the background, not the object itself. So this is the real world demonstration of this quantum stealth technology. They claim to make a military object like a tank invisible by manipulating the light paths, and this kind of demonstration hints that there is a huge potential military invisibility solution coming up, which will change the shape of the modern warfare. Okay. So with that, I'll conclude this lecture on invisibility cloaks. In the next discussion, we'll talk about carpet cloaking, okay, and where it is applicable. So with that, I'll thank you, and if you have got any query, you can drop an email to this email address mentioning the course title and the lecture number in the subject line. Thank you.